We're continuing chapter 8. So the first two sections went over some basic geometry stuff on the law of sines and then on the law of cosines. Next, we're going to be looking at direct applications of those two trigonometric laws in the realm of vectors. Now, vectors are introduced in a geometry level course, which is 2 years before this pre-calculus course, but they're going to be introduced, or they have been introduced in a way that's only geometrically treated. And we're going to be concentrating on that geometrical treatment here in 8.3. We take it a step further in the next section and then turn that into an algebraic understanding of vectors. So we are going to study vectors in the coordinate plane and be able to come up with some sort of a system for giving coordinates for what we call initial and terminal points that can be used to make a vector, a directional vector. So vectors are quantities that are directly used in physics. If you look at the history of it, they actually came about from physics. One of the earliest uses of vectors that I'm aware of would be in Sir Isaac Newton's work. He has a particular book where he introduced his theory of gravity, and in it he had to develop a whole theory on forces, and he understood forces geometrically as what we call today as vectors. So vectors came about from the need to describe quantities that not only have some sort of a scalar measurement, but also have a direction about them. So a force is a perfect example of something like this. A force has an intensity, so how intense a force is, and then where's that force pointing? Where's it acting on? And in what direction is that the brunt or the essence of that force directed towards? So the way we think of these in mathematics first off, and the way that Sir Isaac Newton first introduced them, or when he first worked with them, he thought of them as directed line segments. So you start off with a point A and a point B somewhere, and then we take the line segment between the two, and we'll draw an arrow to show the direction of the flow of the vector. So it's from A to B. So we'll take this as a vector quantity. So we have 2 points, A and B. A is what we call the initial. B is what we call the terminal. So there's a beginning and an end. So it starts at A, it ends at B. So this vector, a lot of the times we give them symbols. We can call it U, or we can call it V. A lot of the times vectors, because it starts with the letter V. And to denote, or to give the idea that this is a vector and not just a numerical quantity, we'll draw a little arrow on top of that to distinguish it from other non-vector quantities called scalars. So the vector V, we can also think of this as A to B with an arrow pointing towards B. So that's another way that we can write the vector geometrically, just like we normally write line segments in geometry, but there's no arrow indicating what the direction of flow is. So it's from A to B. So vectors are kind of like higher order quantities, not just numbers, but numbers with a direction. And we need some sort of a geometrical system to give a direction for them. Now in Euclidean geometry, we don't have a very precise system of saying this is the location and this is where it moves to. Some location to another location given some sort of a positioning scheme. That's where we need a coordinate grid and a set of coordinates. So that's what 8.4 is for. So here we'll just strictly think of the geometrical nature of these things. So what we want to move into, there's two things that we can do. We can talk about scaling this vector and making it longer or shorter, or also changing the direction of it. So let's think of this as vector V. And I'm going to multiply V by some number. So let's talk about the number A times V, where A is just a scalar quantity. So we're going to think of A as being a real number. And the way that we say that A is a real number is like this. A is inside of the set R, where R represents the set of all real numbers. So if we take A and we multiply it by V, we'd like to be able to think of multiplication of a vector by some scalar quantity as possible. So it needs to be possible. Also, not just it being possible, we would like for the multiplication result to also be a vector. So what I'm going to do is I'm going to denote that quantity in red, or let me go ahead and draw that in red first write it as A times V. So A times the vector V. And let's say if A is less than 1 and bigger than 0, so I would say between 0 and 1, then it's going to be some number that's, or it's going to be some vector that it's in the same direction but smaller in length. So it'll have the same, let's say, and this is going to be kind of weird. Let's say we're going to scale it at the point A. So what that means is the center of dilation will end up being at A. So if we take A to be maybe like an origin for coordinates, so let's pretend there's a coordinate system and it's centered at A. So that way there's no discrepancy here. Then we'll have a vector, same direction, smaller length. Now, if A was bigger than 1, so I could probably do that in green. If A is bigger than 1, then this would result in a vector also that starts at A, but then will be a lot longer. Maybe not a lot, but this will be A times V, where A is bigger than 1. So we stretch the vector out. So multiplying by a number that's positive can go one of three different ways. Either A is 1, in which case there's no change to the size of AB, or vector V. If A is between 0 and 1, it's something that's fractional between 0 and 1, then we're going to have something that's smaller in length, and if A is bigger than 1, it's going to scale it larger than what it was originally. So we're thinking of multiplying by a positive scalar. Now if I multiplied this vector by 0, then we would have just a single point. That vector just boils down to a point. What if I multiplied by a negative? So what if A was negative? So if A was less than 0, it would start again at, it would start again at big A, and the negative direction means it's going to be pointing in the exact opposite direction, and by opposite direction we're going to take that to be an 80-degree difference, an 80-degree angular distance between the two, the original vector and the new vector. And then of course, depending on how big A is, so I should have written A is less than 0. Depending on how big the value of A is, then that'll change the length of the vector, but it's in the opposite direction. So that's multiplication by a scalar. So that's something that we're going to be worrying about in the next section. How do we do that precisely? We'll give a definition for vectors in the coordinate plane, and then we're going to go ahead and define what scalar multiplication looks like. So there's going to be a scheme for multiplying by scalars. In geometry, it's just resizing it, but in the same direction. So it's just following a line, and then the value of A is just going to tell me how long or short it is compared to the original. So it's like a ratio. Now let's say I had two vectors. Let's say I had vector u, which looks like this. And let's say we have vector v. I wrote u twice. V, and it looks like this. Maybe a little bit longer. So like that. So let's say we had these two vectors. I would like to add these two vectors. So when it comes to adding two vectors, so I'm going to probably rewrite this over here. When it comes to adding two vectors, there's a geometrical way to do this, and then there's going to be an algebraic way to do that we're going to build off of the geometrical idea. So here's the geometrical idea. When you want to add two vectors, let's say in this case u plus v in that particular order, we'll go from left to right. So we're going to start with u, and then we're going to end up adding v to it. So I'm going to start with u and leave it right where it's at. And what I'm going to do is I'm going to move v, so that way its initial point is on the terminal point of u. And this is going to be the scheme that we're going to use to add these two vectors. So these two vectors, Sir Isaac Newton actually described this in the very, very beginning pages of that book that I was referring to earlier. What you do is you redraw v a second time, and you make a parallelogram out of it, and you draw u again a second time. So this one's v again, this one's u again. So this was v initially. So there's u and v up at the top left and the top right, and then the bottom two that are dotted are just recreations of v and u, so that way we form a parallelogram. So if you do it this way, it actually does form a parallelogram. These end up being parallel to each other. So how do we state that these are parallel? I think it was like two arrows this way And then if I wanted to say that another pair of lines, you just add another set of arrows. So those are parallel to each other. So we have a parallelogram. The resulting addition will be where U started and will be where V ended up. So the initial point of U is the initial point of U plus V. The terminal point of V, after we've aligned them that way, is going to be the terminal point of U plus V. So the resulting added vector, or the result of adding these two vectors together, is that one that's in red. That one in red is U plus V. And that's how we add two vectors. Would that have been the same had I switched the order? So let's say I draw U again. This is U. And then V look like this. Would that come out the same if I had switched the order? I would like to do V plus U. So what's required there? You start off with V. You would generally leave it where it's at, but I might want to move it so that way I could fit it all in the same area of the screen. So I'm going to move it over here. We start off with V, and then we move U, so that way its initial point, it's on the terminal point for V. Would I get the same vector? So maybe not even having to draw the parallelogram, which I'll do it anyway. So if I draw the parallelogram, it's still just the diagonal. So connect those two opposite ends to form a diagonal, starting at the initial point of V, ending at the initial point of U, and this is V plus U. Now if I had drawn this perfectly, maybe copied and pasted the original V into U from the previous one, you would notice that these two vectors came out identical. So what's going to end up being the case is that the order in which we add two vectors does not matter. We call that a commutativity property. So the addition between vectors, so vector addition is commutative. It doesn't matter what order we write them. So I could say U plus V is equal to V plus U. So geometrically, they're the exact same thing. So that's addition. That's vector addition. What about vector subtraction? So let me take the same two vectors, which I don't think I'm going to cut them up and copy paste. I'll just draw them again. So let's say we have U. And then we have V. And I'd like to subtract these two vectors. Now subtraction, just like it works for real numbers, subtraction, it's going to depend what order we subtract two things. So let's say we take U and then minus V in this particular order. So I have to be really careful. What does U minus V look like? So the way addition usually works, U minus V is the same thing as U plus the negative of V. Now we're going to go ahead and define vector addition and scalar multiplication, so that way that does end up working out. So subtraction is basically just addition with the additive inverse. So we're going to add the negative of the other to form subtraction. And that's the way subtraction works anyway with real numbers. Subtraction isn't a real thing on its own. It's just addition by negatives. And negatives is a multiplication concept. So I'm going to move this, and I want to form the negative of V. The negative of V is formed by starting at the same terminal point, or sorry, the same initial point, going in the exact opposite direction with the exact same length. So this right here is negative V. So it's the exact opposite of V, but in its opposite realm. So it's the opposite direction with the same, with the same length. So that way they cancel each other out. If I were to add the two, they would just make the zero vector. So I would very much like to subtract these two vectors. Now we think of subtraction between those two vectors, U and V, as the addition of U and negative V. So all I got to do is add U and negative V together. So I'm going to add these two. And the way you add them is by placing the initial on the terminal of the first. So the initial of the second on the terminal of the first. And then what you do is you draw a parallelogram. Now if you draw the parallelogram, you're going to end up just doing the diagonal, and the diagonal is going to look like this. And this is where it's going to start. So this vector right here is u minus v. So it just goes in the other direction. So it's basically, well, where does this, we can think of these as forces. Somebody's pushing something in that direction this intensely. Somebody's pushing something, the same thing in this other direction this intensely. Well, what's the result of those two acting on each other at once? So here we get that, in this case, subtraction. So there's vector addition, vector subtraction, and then multiplication by a scalar. These are fairly simple concepts if you play around with them. And what we're going to do is we're going to do just a couple of examples, not too many. This isn't a very large section either way. We're going to cut straight to example number 1. Now these problems might take a little long because of the drawing that we're going to have to do. So I'll go ahead and take a look at number 1. So then we're going to have a little bit extra mathematics involved. Find the magnitude of a resultant. So the resultant would be the result of adding or subtracting two vectors. So we have two forces, 32, 48 newtons. So 32 Newton force and a 48 Newton force. Both of these are acting on a point in the plane. So we can think of that maybe like a box. You have two people that are pushing a box, a very, very, very heavy box. One of them is pushing with 32 newtons worth of force, and the other one is pushing with 48 newtons of force. And they're acting on that same box to push together. We could think of it that way. So, and here it's explaining a Newton of force, or Newton is a unit of force. It's actually the SI unit for force. That equals 0.225 pounds, so roughly 0.225 pounds. So if the angle between the forces is 76 degrees, find the magnitude of the resultant force. So we have a point that they are concentrating their force onto. So there are two forces. On that point, there's one coming this way with an intensity or a magnitude, because magnitude is the formal term, of, let's say this one's the 48 Newton force. So that's the magnitude. Then we have another one that's acting on the same point. So that way the angle that's formed by these two forces is 76 degrees. And this one's the longer of the two forces. So from here to here, this one is 48. Oh no, I already drew the 48. I could have left it there and then just changed it to that way that was 36. Since this one's slightly longer than this one, I'll make that one the 36. So this is the 36. It doesn't really matter. What matters is that the degree or the angle between the two, 76 degrees. And they're acting on the same force. So here's the idea. What is the magnitude of the resulting force? So the magnitude of the resulting force. So I drew the initials back here and the terminals over here, if you can see those arrows. So it's going to be kind of hard to see that, and I'm not going to be able to demonstrate the way that I'd like to. The way that we should do this is by drawing the parallelogram, like I said earlier. So you would draw a parallelogram, and the way you would do that is you would recreate both of these two vectors to the best of your ability. Same angle, same direction, same magnitude. So let's pretend that that's actually accurate. Maybe make it a little bit better. So let's pretend that's accurate. So then the resulting force should look this long. So if I had drawn those arrows in a different direction, so the opposite direction, then it would still result in a force that's long, or that is that long. So another way that you could think of it is you can recreate this 36 one out over here. So the 36 Newton, and then you can recreate the 48 degree or the 48 Newton force this way. So 48 this way. So because I read it that they were acting on that point, I drew those arrows into the point. But you can also draw those arrows out of the point as if that's where those forces are pulling that point towards. So you have one force that's pulling that point towards that way in that direction with that intensity, and then you have another arrow pointing in that other direction with that intensity. So I didn't necessarily have to draw it this way. I could have drawn those arrows pointing out of the point, even though it reads that they're acting on the point. So you could take it as if they're pulling the point. So then what you would do is you would recreate those vectors this way, draw a parallelogram, and if you do that correctly, there's a couple of rules for parallelograms, and you have opposite sides which are supposed to be parallel to each other, and if I had drawn that better, then those would look perfectly parallel to each other. Also, opposite sides have the same measure, so if this one's 48 out over here, the opposite of that one is also 48. This one's 36 as a result. And what they want is the magnitude of the new resulting vector. So let me draw that one in red, so you connect the corners from where it started to where it's going to end up out over here. So that's the new vector, and all they want is the magnitude. So not too tough. To find a magnitude, we're going to probably think of this as a triangle problem. So what was the angle that they gave us? It was 76. There's a problem. 76 is this one here. So one thing that we should know for parallelograms is that if that one's 76, its opposite is also 76. Those are congruent. Now another thing you should remember is that if we talk about adjacent angles, so 76 and then this one, those are going to add up to 180. The reason being, it's that it's a quadrilateral. So quadrilaterals, just like triangles have a law about how many degrees fit inside of a triangle, which is 180, quadrilaterals, which are four-sided figures, have a similar law. There's actually one big law depending on how many sides you have, and you can plug in the number of sides into the formula and it's going to spit out the number of degrees total. And for a quadrilateral, 360 degrees. So what ends up happening for a parallelogram, adjacent or consecutive angles are supplementary. They both add up to 180. So if that's the case, this is 104 degrees. So that's the major takeaway from the properties of parallelograms that you should have seen in geometry. So that one's 104. So the way it's already set up, it looks like a problem that we saw in the previous set of notes, or in the previous section. So this looks like I can apply the law of cosines. So here I have a triangle, it looks like, and I'm going to look at the bottom triangle. The bottom triangle has an angle, an included angle of 104 degrees, and then those two sides that make up that included angle, 48 and 36 in length. So this will work just like a geometry problem. What we really want is just the opposite side length. So we're looking for the length of that side. So now I'm going to forget about the parallelogram and think of it only in terms of a triangle, a single triangle. So if you remember, law of cosines, little c squared is equal to little a squared plus little b squared minus 2 times little a times little b times cosine of big C. That is the law of cosines. The only thing I'm missing here is C, technically. A is 36, B is 48, big C is 104 degrees, it looks like. So c squared, which I don't know, C, that is supposed to be equal to 36 squared plus 48 squared minus 2 times 36 times 48 times cosine of 104 degrees. And at this point, all I need to do is find out what the value of C is, and we can go to the calculator. So it's C is equal to the square root of all that stuff, which I can just point in here, which is approximately, and they didn't tell me what to round to. I'll round to the nearest Newton because they have it in whole newtons. So 32 and 48 with no decimal value. So 2 sig figs, more than likely nearest one's value. So I'm pretty sure that I'm in degrees. So you want to make sure that in your calculator you're in degrees, or you want to know what mode you're in and then work accordingly. So we want the square root of 48, actually no, 36 squared plus 48 squared minus 2 times 36 times 48 times cosine of 104 degrees. And I get 66 point, in this case 6, and we're supposed to round that, no? So 67 newtons roughly. So I'm using the same rounding scheme, or the same number of significant digits. In this case, 2 significant digits, so approximately 67 newtons. And because that side length c is exactly the magnitude of the vector that they want, that's the answer for number 1. So it boils down to a law of cosines problem. You end up getting some sort of oblique triangle, and you can solve an oblique triangle most of the times using just the law of cosines. So this is like an extension of the previous section, just applied to some new geometrical idea vectors. So that's number 1. We're going to move on. Equilibriant. So the equilibriant, that's a fancy term for what I drew out here. I don't know if I still have it. I still have it, but where's it at? Here. So we talked about the negative of a vector, and I cut it out. But we're talking about the equilibriant of a vector, and that's also known as the negative of a vector. So if you have some vector u, let's say it looks like this, the equilibriant of a vector is the vector that when added to the vector, you get the 0 vector. So in other words, equilibrium. So if I draw it from the same initial and then draw it so that way it has the exact opposite direction, this is the equilibriant of u. But that happens to be the negative of u. So the equilibriant, the one that when you add it to the original, you get 0, will be its negative. So the equilibriant of a vector v is the negative, or a vector u, it's the negative of the vector u. So here's what we'll do. We'll look at number 2. And for number 2, find the angle of the equilibriant of forces, 54 newtons, 42 newtons, acting on a point A. If the angle of the forces is 98 degrees, then find the angle between the equilibriant and the 42 Newton force. So we will draw those two acting out of a point. So here I have a point, and they called it A. And there are two forces, 54 newtons and 42 newtons, that are acting on it with an angle of 98 between the two. So 98 degrees. Let's say this is the 54. And then 98 is going to be kind of a wide angle. It's a little bit bigger than a right angle. And let's say this is the 42. Okay, so if I had kind of drawn that correctly, then we should be able to figure that out, no problem. Let's see. We want to find the angle between the equilibriant of those two forces and the 42 Newton force. So we want the resultant first, and to find the resultant, parallelogram. I'm kind of bad at drawing those. But let's say that's where the terminal side is going to be. This is the equilibriant. Or sorry, that's the resultant. So the resultant is what happens when I add those two vectors. We want the equilibriant of that vector. So the equilibriant of that vector will be the same length, starting from the same initial, and then it's going to end up in the opposite direction. So this right here is the equilibriant, which we can call that one, I guess for equilibriant, I'll call it E, uppercase E. So the equilibriant of that force, which we can call it F. And we want the angle between that equilibriant and the 42 Newton force. So we want this angle. That would be nice. So how do I find out that angle? So maybe the way that we can find that angle out is to find this one out and then subtract it from 180, since the equilibriant and the original are supposed to be straight, or are supposed to form a straight angle. In other words, 180 degrees. So that's probably the way I want to go about that. Now what they did give me, however, is that the angle between these two forces is 98 degrees. So I might want to find out what this angle is first off by using the properties of parallelograms. 98 and that one are supposed to add up to 180. So 102? No, sorry, not 102. 82? That was way off mathematically. So that's 82 degrees. So 82 plus 98 is going to be 180. So that one I know for sure is 82. So let's see. I want to find out what this other little angle is. And to find out that angle here, I'm probably going to need to use law of cosines or law of sines. So what do I have? I know this one for sure over here is 54 newtons. I have two sides and the included angle. So, and that's it. So I'm going to need to use probably the law of cosines. And I could use the law of cosines to find that one out. Which we didn't need the magnitude, but we're gonna end up needing it anyway to get what we want. So let's see. I'm gonna call that one C. Yeah, we can call it C. C squared is equal to 42 squared plus 54 squared minus 2 times 42 times 54 cosine 82 degrees. Plug that into the calculator really quick. We're gonna get C is equal to, so C is equal to square root 42 squared plus 54 squared minus 2 times 42 times 54 times cosine 82. I'm in degrees. I'm getting roughly 63.6295. That's as many digits as I can show based off of my calculator. So that's going to be in newtons. And how come I'm not rounding this? That's not my answer, so I don't need to. I'm better off not rounding it. I want as many decimal points as I can get to make the other parts of this as accurate as possible. Then at the very, very end, we'll round. So we rounded earlier because that was the information they wanted. So that was the last thing that we were supposed to deal with, and then we go ahead and round it because it's the last part of the problem. This is not the last step of the problem. So what do I want? I want this angle, which I can call that angle, let's say theta, from here to here. So that angle's theta. How do I figure out theta? Well, I can set up a law of sines ratio, I think. Sine of theta divided by 54, because we're talking about opposites, must equal to, now I'm going to use the ones I have, sine of 82 degrees divided by what we just found, 63.6295, because that's the one that's opposite of that 82 degree angle. So here I'm setting up a law of sines ratio. We're going to solve for sine theta. So you would just need to multiply by 54 both sides. Sine theta is equal to 54 sine of 82 degrees divided by 63.6295. Then to find theta, theta is equal to the inverse sine of all of that, 54 times sine 82 degrees divided by 63.6295. Plug that into a calculator. My calculator's in degrees. Inverse sine 54 times sine 82, outside of parentheses, divide that by 63.6295 inside the outer parentheses. And I'm getting theta equals 57.1828. And I think I'm almost done. What was the strategy that I was going by, or what was my game plan? If you take E and F, those two forces, which one of them is a resultant force, the other one's the equilibriant of that resultant, those two form a 180 degree angle. And because they form a 180 degree angle, I know that the angle theta is 57.1828. The other angle that we were wanting, which is the angle between the resultant, or the equilibriant of the resultant, and the 42 Newton force, that's just 180 minus that. So then the one that we want is 180 degrees minus the one we have, 57.1828. And that would be what? 132 point... I would probably want to round anyway to the nearest degree. It's going to end up being 132 degrees if you round it. So it's 132.8172. But you would round that up just to 132 degrees. And that would be it for this particular example number 2. That's kind of a tough one, especially since I didn't have a drawing. I don't know if you caught it earlier, but I have a box here, and that's hiding the drawing that was already there. So that took the fun out of it. I would rather draw all that out. So it would have been a lot easier if we didn't have to draw it, but it's much more instructive, and you learn a lot more when you have to draw these things yourself. And that's it for number 2. And really that's all I'm going to want to go for or go over for this particular section. There's not much more. There's 2 other problems, but these are, again, just right triangle problems or oblique triangle problems. It's more of the same. So these 2 are more than enough and good enough for now, and which we should already be ready for 8.4 in the next video.